Hello, my name's John Linz, and today I'm going to be talking about artificial neurons, how they work, and hopefully this video will sort of give you a higher level overview of how neural networks work. My goal with this is to create a short video series, and hopefully at the end you'll have a much deeper understanding of how these things work and why they're useful. But in order to do this, we have to compare functions and regressions. Because remember, neural networks are sort of like regression machines in a sense, and I'll get more into that. But first, let's compare these two things. So on the bottom left, we have a diagram of a function. You can think of it as a mysterious box where it's actually not mysterious at all because you know what's inside it because you can give it an input and it gives you an output. Regressions, on the other hand, they actually are mysterious boxes, but you have to construct the box yourself. You're given inputs and outputs, or x and y values, and you're actually trying to construct your own function from these values. You can actually do this on a graphing calculator. There are various programs that can help you do this. But basically the idea is that you don't know what the function is, but you know the inputs and the outputs, and you construct a function based off of that. And there are a variety of different functions, not functions, of different regressions out there. Basically the idea is just to create a line of best fit. So on this slide, I've put a diagram of what a linear regression looks like and a quadratic regression. But there's a plethora of different regressions out there. There are sinusoidal regressions. There's a ton, basically. But for more complex regressions, you're going to need a neural network because there is not a pre-programmed regression algorithm for that. So you're going to need a neural network to sort of fit a curve to your data, essentially. But I'd actually like to play a game with you where I can my goal is to prove to you that there's a neural network inside your head doing regressions. And now, of course, these examples could easily be computed by a graphing calculator, but it's just to show you that your brain can do regressions, and that this is what a neural network can do as well. So given these inputs and outputs, or x and y values, construct a function based off of these. Now when I look at this, I've observed that it's 1 times 2 is 2, plus 1 is 3, 4 times 2 is 8, plus 1 is 9. So it would be reasonable to assume that the function here is 2x plus 1. And I'm right. Here's another one if you'd like to try it. You can pause the video. The answer is x to the power of 5. But yeah, basically, your brain can do regressions, and neural networks can as well. More complex regressions, that is. Okay, so now let's actually get into artificial neural networks. In order to do this, we have to break it down and focus on just what a artificial neuron is. So it's actually pretty simple. It starts by initializing a vector of weight values. And to start, they're actually random. They're just randomly generated values. And then secondly, you have to have an input vector of some sort. For example, if you're trying to classify images, maybe you're trying to classify cats and dogs, or images of cats and dogs, what you can actually do is you can create a vector from the image by measuring its grayscale value at each pixel, and then inserting that into the vector, and you'll basically just have a vector of floating point numbers ranging from 0 to 1, and you can input that into the neural network. Now, what actually happens is you compute what's called the dot product, which you can see here, which is just the idea of multiplying each dimension in the vectors together and then adding the products. So you can think of it as you're inputting two vectors and you get a single number. You then add a bias to this number, although that's optional, and then you take the result of that and you insert that in as an argument into the activation function. Now, I'm going to go into what activation functions are in a following video, but just think of it like this. The activation function determines the final output of your node or neuron. In other words, it is the deciding factor in whether a neuron should fire or not. And then here is, it's basically the same as the previous slide, although it's in a more familiar mathematical notation. As you can see, this is the input vector, and this is the weight vector. You're taking the dot product of the two to get a single number, which is v, and v plus the bias is inserted into the activation function as an argument to get your final output, y. Okay, so now that you know what a neuron or a node is, how do you actually put these nodes or piece these nodes together in such a way that you can create a neural network? So you do this by creating layers. Now, I should probably mention that the layers in the middle, the layers between the input and the output layer, are called hidden layers. And I put down here that if you add enough hidden layers, your neural network becomes what's called a deep neural network, which are extremely powerful and they're widely used. You should also take note that the output of the previous layer becomes the input of the following layer. That's at least the case in a fully connected neural network. Okay, and then the question arises, how do these models learn, or how do these neural networks learn? So this is when it gets a little bit more complex, but not really. Basically, you construct a function with loss on the y-axis and every possible weight on the x-axis. And your goal is to find the weight value that minimizes the loss. And this is called gradient descent. And once you find the weight that actually minimizes the loss, you want to go back to each node in the neural network, and you want to tweak its weight value. And you do this over and over again through the iterative training process. And by the end, you'll actually have a trained neural network that gives you a valuable output. Because remember, to start, the weights are randomly initialized. So if you were to give your neural network a picture of a cat, well, there's a 50% chance that it's going to say that it's a dog, right? Because it's just random. And then through the training process, you actually compare the output that you got by your preferred output. So for example, if you get a dog, when you really inputted a picture of a cat, you recognize that, you compute how wrong it is, or you compute its loss, and then you try to find the weight value that minimizes that loss, so that the next time it'll actually predict the correct output, right? If you input a cat, it tells you it's a cat. If you input a dog, it tells you that it's a dog. I'm John Linz, and stay tuned for the next video. So have a good one.